this video we're going to be going over a convection example. So we'll be using a few equations and we'll just get right into it. So a pipe with an inside diameter of 92 millimeters and an outside diameter of 128 millimeters carries saturated steam at 350 degrees Celsius over a distance of 65 meters. The thermal conductivity of the pipe is 47. The pipe loses heat to ambient air at 7 degrees with heat transfer coefficient of 21. Calculate the rate of heat loss from the pipe. So we've given quite a lot of information if we write it down on our pipe diagram. So we have an inside diameter. I'm going to change all of these to SI units. So SI units of length are meters. So 92 millimeters times 10 to the negative 3 is converted to meters, right? Because there are 1,000 millimeters in a meter. So if we do the same for the outside diameter, 128 times 10 to the negative 3. 10 to the negative 3 means divide by 1,000. And it carries saturated steam at 350 degrees Celsius over a distance of 65. So we assume the pipe is 65 meters. The thermal conductivity of the pipe is 47. Pipe loses heat to ambient air at 7 degrees, so we have, just assume this is air around, with heat transfer coefficient of 21. Calculate the rate of heat loss from the pipe. So we've added all of the information to our diagram and we're ready to apply the equations. So we have some equations for the convection, but in this problem we have conduction and convection because the saturated steam in the pipe, it conducts through the pipe, and then you have convection from the pipe wall to the air. So you have to take into account the conduction as well. Examples on how to do this are in a previous video. So we'll start with the equation for heat transfer. We have delta T, which is the change in temperature, over R. Because we're taking into account conduction and convection, this would be R total. So change in temperature we're given was 350 degrees of the saturated steam and the 7 degrees of the ambient air. So 350 minus 7 over R total. R total is the resistance from convection plus the resistance from conduction. Now if you watched the previous video, resistance for a circular pipe can be calculated from the following equation using the natural logarithm. So we'll be using this as well as this equation here. So R total is 1 over HA. This is convection. And this is the conduction part. So if we plug in all of the numbers we're given, we should be able to calculate the resistance. So we have heat transfer coefficient, which was 21, multiplied by the area. So because it's convection, the convection happens on the outer surface of the cylinder. So we need the area of the outer surface. We can calculate that by using the diameter and the length. So we would use pi d to get the circumference and then multiply by the length. So multiply by pi times the diameter times the length. So this would be the area. And then we add the distance from conduction. So we have natural logarithm plus the radius of the outer diameter, the radius of the outer cylinder. So it would be 128 times 10 to the negative 3 divided by 2, and then that's divided by the inner radius. So 92 times 10 to the negative 3 divided by 2, and then that's all divided by 2 times pi times the thermal conductivity, which were given as 47, and these are all in SI units except from the millimeters, and multiplied by the length, which we were given as 65. If we calculate the total resistance, we put it all in the calculator. That gives us a resistance of 1.84 times 10 to the negative 3. Then if we plug that back into our original equation for heat transferred, we get 186,511.1, and that's in watts, yep. So joules per second, and that's it.